Hello everyone. Today we're going to talk about the new topic of predicate logic. In this section, we will see what is predicate logic, and it's about the quantifiers. Okay, so that will be a new terms for you. You can express in logic. And then we will talk about logical equivalence as well, and then nested quantifiers, because you will see more complicated form of logic. And then we will try different examples, try to translate from logic, practical logic to English and vice versa. Next, let's see section 1.4, predicate and quantifiers. Just like propositions, we will see what is predicate logic and what are all those variables and quantifiers. And then we will see how to negate in quantifiers and translate to English sentence. Let's see the motivation. Why we need practical logic? Why we just use propositional logic? Why it is not enough? Let's see this example. If we have two sentences, all men are mortal, something is man. So mortal means people are not living forever. People will die in the end. So that means all men have to die in the end. Okay, that's the meaning of the word. And Socrates is a man, so you can see this man could mean all men, right? So does that mean Socrates is mortal? Socrates has to die in the end. Okay. So based on propositional logic, we cannot have such inference. But if we use practical logic, then we can infer different results. Okay, so that's the reason we need to study practical logic. Next, let's see the definition of practical logic. Actually, we have three terms that compose of practical logic. The first thing is variables. Just like we use positional variables, here in practical logic, we also have such variables as well. And then we have the declarative sentence. Here we call that predicate. Okay, so we can describe the properties of the subjects. And most importantly, we have quantifiers to explain the extent which the predicate is true within such range. Okay, so let's see the example of how we propose practical logic. Once we have the sentence x is greater than 3, so you can see x is a variable or subject, and then we have the declarative sentence is greater than 3. Okay, that's our predicate. And then we can use p of x to indicate that's kind of function because once we have the predicate, you can replace any instance into the variable x. Okay, so you can say maybe Professor John, no, not Professor John, or maybe 100 is greater than 3, or 10 is greater than 3. Okay, so if you replace x by 100 or 10, then this sentence will be a proposition, right? But x is greater than 3 is not a proposition. We don't know what x is. So you can consider this as a function, propositional function. Once we replace x to any number into this predicate logic, then it becomes a proposition. So you can see it's more flexible. Once we use predicate logic, then we can express very general terms using variables. And then we can replace the variables by any instance within the extent, then we can make it a proposition. Okay, so we can see generalization of propositions. That's predicate logic. Okay, actually, we just need to replace the variable by any elements by the domain we have defined. Right, let's see the example. What is propositional function? So let Px0 x larger than 0 and the domain is integers. Okay, next we can verify once we replace x by any integers, then what happened? For example, p of -3. -3 is within the range of integers, right? So -3 larger than 0. This is incorrect. So the proposition is false. And p of 0 is false. P of 3 is true. Okay, so based on the definition of predicate logic, we define the quantifier, we define the predicate, and we can replace and reduce any propositions. Alright, so this is another example, x plus y equals z, and we use u for our quantifier. So once we have 2 times 1, 5, we can determine the true false of this proposition. But if we have x with z, then it's not a proposition. Okay, once we know this, then you can see what we have learned from propositional logic. We can migrate the concept to predicate logic, such as we can use different connectives. So we can see P of 3 or P of -1. So once we have the predicate logic of Px is 0 for all integers, then we can determine the true or false of these compound propositions. Alright, so most importantly, the most difficult difference from predicate logic of propositions is the quantifiers. So let's focus on the quantifiers. So we talked about the example, all men are normal scientists of some cats do not have fur. So when we talk about all of them or some of them, we can define different quantifiers. We call that universal or exclusive. So we use the symbol, this one, that means for all elements within the range. Or we can also say for some exists, some instance, then we can write the notation of this for all x p of x or for some x p of x. Okay, so maybe you can distinguish from these two predicate logic. If we call that for all x p of x, that means you can examine all elements one by one within the domain. That makes p of x. So when we say for all x p of x, that means every element within the domain that p of x is true. Okay. We write for some x p of x true, that means if you can find one or more instances, so if you can find only one, that's okay. Okay, within the domain, once you can find some x that p of x is true, then you can assert for some x p of x. Okay, next, let's use this example to verify the concept of for or and for some. Okay, so let's see, if p of x denotes x larger than 0 and u is integer, our domain is all integers. Then for all x p of x, okay, it's false, because for all integers we have 0, we have negative integers. So if you try every element to this predicate, then you can see p of x is false, because we have a lot of elements that p of x is false. Okay, but if we change the domain u to positive integers, then p of x means x larger than 0 for all x p of x is true. Because if our domain is positive integers, you can try 1, 2, 3, 4 to infinity. Okay, then you can see for all x, p of x is true. Okay, so if p of x denotes x is even and u is integer, then you can see for all x, p of x is false. Because we have 1, 3, 5, that is odd number. Okay, so this is for all. Let's see for some. Okay, for some x p of x, sometimes we can call that there is an x such that p of x, or for at least one x p of x. So you need to only find one example within the domain that makes p of x is true, then you can assert for some x p of x. Okay, let's see this example. We use the same predicate as larger example, and u is integer. Then for some x p of x, this is true, right? Because you have a lot of examples. 1, 2, 3, 4. If you can find only one example, then that makes for some x is true. If p of x is x and u is positive integers, okay, then you cannot find any one instance to make p of x is true. Because when we have positive integers, we need to try from 1, 2, 3, 4. But all of them are larger than 0. Okay. So once you have tried all elements within the domain, you cannot find any example to make it true, then for some x p of x is false. Okay, so based on the previous example, you can see how we determine the predicate logic for all or for some, it is true or false. Actually, if we have for all x p of x, you need to loop all elements within the domain to see if every element makes p of x is true. If we really do, then we can say for all x p of x is true. If for some step we find a particular element that p of x is false, then that makes for all x p of x false. Okay, so similarly for some x p of x, we can also look for all elements within the domain. Once we can find one particular element to make p of x is true, then we found that element. So for some x p of x is true. What makes it false? You look all the elements and you cannot find any element to make p of x true, then we just assert for some x p of x is false. All right, next let's see the priority of quantifiers. Actually, this is very important because people make a lot of mistakes when they write predicate logic. The quantifiers for all and for some have higher priorities than the logic operators. Okay, so that means for all and for some, it has the highest priority among all of them we have learned for logic operators. So if we write for all x, p of x, or q of x, so we know the priority of for all is higher than or. Okay, so this actually means for all x, p of x, parentheses, or q of x. Okay, but if you want to represent the meaning for all x, that it follows the property p of x and q of x, then you need to parentheses. Okay, so actually you will see a lot of examples. We are actually assert for all x that follows some properties. Then you need this parentheses. Okay, once you don't have the parentheses, then the meaning becomes this. Okay, then you will have totally different meaning. Okay, next let's see the example how we translate from English sentence to logic. So every student in the class has taken a course in Java. Okay, so once we have seen the English sentence, do is to define the domain. Because the definition of domain is different, then you will have different results of practical logic. So let's see how we define domain. If we demand that U is all students in the class, and J of X means X has taken the course in Java, then every student in this class has taken the course in Java. We can simply write for all X, J of X. Because the definition of X is all, the domain is all students in this class. We already have the domain, all students in this class, then all students has taken Java. Okay. So that completes the practical logic. But this is the simplest case. Usually we won't define the universal as all students in this class. Usually we define the domain as all people. Okay. So next we need to define different practical logic because we need students in this class and student take the course in Java. Okay. So if the domain is all people, then we can define S of X is X a student in this class. And then we also have J of X as taken Java. Okay, so we have for all X, if Sx then J of X. That means for all people in the domain, if he is a student in this class, then he has taken Java. That means all students in this class has taken Java. Right? If you are a student in this class, then you take Java. Then that means all the students in this class has taken Java. Okay, next I want to think of the other expressions. Why this practical logic has different meaning than this question. Okay, we have for all X, S of X, and J of X. Why this expression is incorrect? For all X, all people, S of X means X is in the class. J of X means X take the course in Java. Why this meaning is different from Java? Alright, let's see what this practical logic means if we have all people within the domain. Okay, that means for all X, all people. S of X means all people in this class. Okay, so all people in this class. And all people has taken Java. All people also take the course in Java. Okay, so this is the Venn diagram when we consider the set. Okay. Then that's different from the original question, right? Every student in this class has taken Java. Actually, it means we have all people here, but we have some people in this class, and all of the students in this class have taken Java. Okay, so you can see actually this one has totally different meaning than this one. Is that okay? Alright, next let's see the other example when we use for some. Okay, some student in this class has taken a course in Java. Okay, not all students, just some student in this class has taken a course in Java. If we define the domain U for all students, then we can simplify for some X, J of X. Because our domain is already all students in this class. and we can as well for some X has Java. But if we have the domain for all people, then we can write for some students x of x and j of x. That means among all people, sum of x is a student in this class, and he also takes the course in Java. That means this student has in this class, and he also takes Java. That follows the original description. Some student in this class has taken the course in Java. Right? So, is that okay? All right. Next, I want to answer the question why this expression is not correct. This sentence. If you write for some x, if s of x, then j of x. This expression is wrong for this sentence. Please write down your answer and explain why this practical logic is not correct for some students class as taken course.
好，那没问题，那下课再试试看好了。
If you have the answer and you think your explanation is correct, you can raise your hand to share your answer to the other students. And if your answer is correct, I will give you 1 extra point. All right, anyone? Okay. We have for some x. So among all people, we have 1 x. Mhm. But some students may not take the course in Java. It's okay. Because we only have some students in this class take the course Java. So if you have other students in this class do not take Java, it's okay. Right? So what happened? What's wrong for this expression? No. If you write for all x,
then that all students in this class take Java. But I write for some X. It's not all X. The domain is all people, but our practical logic is for some X. Among all people within the domain, we have some X that follows this property. Mm-hmm. Mm-hmm. Mm. Why it is not correct? Because what you said, if he is in this class, he has to take Java. That means some student in this class has taken Java. It sounds like correct. Okay. Okay. Mm-hmm. Okay, very good. Okay, let's see uh, how we explain this is incorrect, because this is conditional statement, right? So we know the truth table of a conditional statement. If P then Q, and if P is false, no matter what the truth value of Q, that makes all conditional statement true. So maybe we can discover one example. If Sx is false and J of x is true, then let's see what happens. Okay, so we have the universal all people, and then maybe some people is in this class, but we need to discover one x that is not in this class. So maybe this instance we call that A. Okay, so because this is class, A is not in this class, but A takes Java. Okay. Then we can see if A is not in this class, but he takes Java, that makes the expression true, right? But you can see this is totally different from the original meaning. Some student in this class has taken Java, right? So we have the Venn diagram. If this is all people, then we have some student in this class has taken Java. Some of the students do not Java. So the original meaning should like this. But we discover one example that follows this diagram that makes this true. Okay. So you can see the meaning is totally different from this one. Okay. So this is not a correct practical logic for this sentence. Okay, I hope you can remember these two counter examples, because next time when you write practical logic for all and for some, if you can remember this example, why this is wrong and why this is wrong, then I believe you can write correct practical logic for the following example. All right, after that, let's go back to the original example. So if we have the positional function, then we can plan all men. So then we can have the position men of x. Okay, x is a variable you can replace by any instance within the domain. And we can also write immortal of x. That means the variable of x is immortal. And we can replace the original English sentence, all men are mortal. So we have we have the missing parenthesis. If we want to say all men are mortal, then we need to say for all x parenthesis, if x is man, then x is mortal. Okay, so once we have this expression, then for all people within the domain, if he's a man, he's not a woman. Okay. Okay, if he's a man, then he's mortal. That means all men within the range is mortal. Okay, and Socrates is a man, then we can replace the instance directly into the practical logic. So, man of Socrates means Socrates is a man. Okay, and then we can rewrite the conclusion. Socrates is also mortal. He has to die in the end. So, mortal of Socrates. Now we can see we can express the practical logic using for all and for some. Then we can follow the propositions using the connective and compound propositions. Okay. So after that, we can see in next sections how we can derive the conclusion based on two premises. Now we haven't been learning yet, but stay tuned. All right, so we have different thinking of quantifiers by conjunction and disjunction. If for all x p of x, actually you can think of all of elements follows the properties, and we apply the conjunctions for all propositions. So for all x p of x, if we have all elements within the domain 1 to 3, then to make this true, we need to have P1 and P2 and P3 is true. That makes for all x p of x true. If we have for some, then we can rewrite P1 or P2 or P3. Either one of it is true, then that makes the overall practical logic true. Then for some x p of x. All right, next let's see the negation of quantifiers. Okay, so if we consider for all xj of x, and we want to negate this sentence, so actually it means it's not the case that every student in the class has Java. If not everyone in this class has taken Java, that means by someone who has not taken Java. Okay. So actually, we can use for all xj of x. It's not the case, so this is the negation of the original sentence. So actually, we can rewrite to for some x not j of x. If we can find someone in this class who is not taking Java, then we are just have the negation of the original sentence. Not everyone in this class has taken Java. So they are equivalent form. Okay, then next let's see how we negate for some xj of x. Okay, if we have one student in this class who has taken the course in Java, then the negation is it's not the case there is a student in this class has taken the course in Java. So we have no student in this class taken Java. So if we have the negation, that for some x j of x, actually it means for all x not j of x. If all students in this class has not taken the course in Java, then you cannot find any instance, any students in this class who take the course in Java. So we have one x j of x. Okay, actually, this is just the
Morgan's law for quantifiers.
If we have the equation and we have practical logic, actually we can consider very similar concept to the Morgan laws we have learned. We have the negation here, and we can distribute the negation to all components later. So for some x, it becomes for all x. For p of x, if you distribute the negation, then we have non p of x.
All right. Next, let's see the example. Some student in this class has visited Mexico. Okay, so we can define if m of x means x has visited Mexico, and s of x means x is student in this class. So we already have seen this example, right? In the universal of all people, some is in this class and some has visited Mexico. So we can write for some x, s of x, and n of x. If we can find that one, that means x is in this class and x also visits Mexico. That means for some x, for some student in this class has visited Mexico. Alright? Next, every student in this class has visited Canada or Mexico. So now we have Canada, so we add additional propositional functions e of x. That means x has visited Canada. Okay, remember, every student in this class means if S is in this class, then S must visit Mexico or Canada for all of X. Okay, if we have for all of X, if he's in this class, then he has visited Mexico or Canada. Then that means every student in this class has visited Canada or Mexico. All right, is that clear for everyone? Because finally, lastly, we will have a series of tasks for you to examine your concept is correct or not. All right, let's see this exercise. Now we have three different things in our universal domain. We have LEGO, Nerd, and Thingamabob. Okay, so if you Google what is LEGO, you will see that one. So that's have two characters. Okay. Then what is nerd? Anyone knows what is nerd? What do you think about? Okay, if you don't know, that's okay. Because it doesn't matter. So we can just write if x is legal, then we write f of x. That means x is legal. And s of x means x is nerd. And p of x means x is about. Okay, and then translate everything is of legal. Please write down your answer on the paper. It should be easy, right? Okay, what's your answer? Okay, good. For all x f of x, it means everything within the domain is f of x. Everything is legal. Okay, next I see nothing is a snare. Please write down your answer. That means you examine every instance in the universal, in the domain, and every element is not snurred, right? Okay, you have finished your answer. Okay, what's your answer? 不用讲了，讲给大家听吗？就是你可以讲存在啊，或是自己所有，for all for some 都可以，还是你有什么特殊情况讲出来？那那你看看吗？Okay, not for some s of x. So let's see. So that means there doesn't exist any x. It is s. S means x is none. So that sounds correct, right? So we don't have any x that is x. That means nothing is none. Alright, so based on the De Morgan's law, actually you can write the other form. For all x not s of x, you can examine every instance in the universal. Then if it is not s of x, that means for all x, all of them are not snurred. That also means nothing is snurred. Actually, it's the equivalent form based on the Morgan's law. Alright, next one. All Legos are snurred. Please write down your answer. That's very similar to all students in this class that has taken the course Java, right? So if you want to assert all Legos are snurred, okay, you have finished your answer. Please. Hello, everyone. Could you hold my phone by yourself? Okay. So let me repeat your answer for all x f of x, then x of x. Right? Is that your answer? Okay. So anyone has different answer from here? Of course. So it's already x. F of x. And x of x. Okay. Do you have different answers from the other two students? Okay, what's your answer? For all x. F of x. F of x of x. And any different answers? Okay, you have the fourth answer. Okay. For all x. So f of x. X of x. Okay. So do you have different answers from this form? Anyone? So you have all the same results for either of these, right? Any other? Maybe they are all incorrect. And your answer is correct. Do you have different answer for the other students? Okay, so let's see. I just give you a hint, right? So if you compare this example to all students in this class has taken the course in Java, that tells us actually this one is correct. Okay, so for all x, if x is legal, then x is nerd. That means all legals are nerd. If he's a legal, then he's a nerd. Then that means all legals are nerd for all x, right? So maybe we can compare to the first one. The first one misses the parentheses. That means for all x f of x, then s of x. Okay. So I say it has different meaning to this one. Okay. So this is not correct. How about this? What is this? For some x f of x and s of x means we have the universal. We have a lot of candidates. Then you can find one x. He is legal and he is. Then maybe the expression is some legal is. So that's what this means. Okay. And what is this? Okay. For all x, f of x, and s of x, assume we have the parentheses here. Okay. So that means for all x, everything within the domain is legal and is also snurred. So that's different, right? Because we have said that this is the universal. This tells us everything in the universal is legal and snurred. But it's different from this sentence, right? This sentence is if he is legal, then he is also snurred. Right? So we have the other elements, which is maybe sigma bar. We have sigma bar here. If he is legal, then he is nerd. And this one is everything is legal and everything is nerd. So we have different meanings from this one to this one. Okay. All right. Next, let's try this. Some legals are sigma bar. This should be easy, right? So maybe you can think of the example. Some student in this class has taken the course in Java. So it follows two different properties. Okay, what's your answer? Some x 括号 f of x p of x. Okay, so if you can find some x is legal in sigma bar, that means some legals are sigma bar. Okay, so it sounds correct. Okay, next one. No snurd is a sigma bar. Okay. So maybe you can think of if no snurd is a sigma bar. So you need to examine every element within the domain. And if it is nerd, then it is not sigma bar. If every element found that condition, then that means no nerd is sigma bar. All right. How about you? All right. Any other different answers? For x, wow, x of x, y, not t of x. Okay. Any other different answers? All x, wow, x of x implies t of x. All right. Any others? Okay. All x, wow, x of x implies t of x. All right. I believe you have more answers, right? Let's give me one additional answer. Anyone? For all x, wow, x, x of x, t of x. All right. Now we have so many different answers. Okay, which one is correct? Okay. Maybe we can think of intuitively from this sentence. No nerd is a sigma bar. That means if you evaluate every nerd, then if he's a nerd, then he's not a sigma bar. Then that means no nerd is sigma bar, right? Okay, so what we can write. Okay, the first answer is we can write there does not exist x of x, and p of x. Okay, because this means we have some x is not in this above, but it's not the case. There doesn't exist any x is above and is okay. That means no node is a sigma bar. Of course, we have its equivalent forms once we apply De Morgan's law. Okay, if we move the negation backwards, then we have for all x, not x of x, and we transform conjunction to disjunction and not p of x. Alright, and then we have something or something. Remember, we have if p then q, that equals not p or q. So not p or q, that means x of x implies not p of x. Okay, so what I mentioned earlier, the very intuitive way is to think of if p is third for all x, if he's third, then he's not above. That
means those never exist in Java. But actually, you can transform to two other equivalent forms. Okay, so you can see this one is correct, right? And we have this one is correct. Okay, and then we have okay. So the other side, okay. All right. So let's see a more compound expression. If any flagle is a snare, then it's also a sigma bar. So you need to know the meaning of this sentence first. Does that mean for all or for some? If any flagle is a snare, then it's also a sigma bar. So does that mean for all or for some? For some. For some, really? Does that mean we have exist flags if it's not the base of sigma bar? Or is all every flag is not the base of sigma bar? We need to distinguish the meaning of the sentence first. All right, I will give you one extra point if you answer this question correct. Okay? For all x, 两个括号 f of and s of x 括号 t of x. Okay, so let's see. Actually, it's a conditional statement. If P then Q. Okay, that means for all x, if x is legal and snare, then it's a sigma bar. Okay, so it also means so by this time, for all x, if it follows f of x, then it will be t of x. That means every legal, if any instance x is legal in snare, then it will be sigma bar. Okay, it sounds correct. Okay. Okay, very good. One extra point. Go to TF the class. Okay, I hope by this exercise you can distinguish the concept for all and for some, and then use the correct form. Just remember the counter examples for all and for some. And when you write the different forms, then the meaning changes. All right, next let's see another examples for system spec. Okay, so we can use predicate logic to design a very complicated system spec using different variables. So let's see this example. Every mail message larger than 1 MB will be compressed. Okay, that makes sense because larger emails
very large email will be compressed.
And the second one, if a user is active, at least one network link will be available. Okay, that's system spec, right? Because we have active users, so we must provide available network links for that user. Okay, so let's see how we write this sentence into predicate logic. Okay, for the first sentence, mail message larger than 1 MB. Okay, so maybe we can use mail of my. That means the mail message m larger than 1 MB. Okay, so we have mail of my. We have the subject or variable m to indicate different mail messages. We have y to indicate different size. If we write 1, that means 1 MB. 10 means 10 MB. And then we also have compressed. Okay, so we have C of M to indicate mail messages will be compressed. C of M. Okay, so that will be the position predicate logic for the first sentence. And then let's see the second sentence. We can define A of U, that means user U is active. So we use capital A to make the user U is active. Okay, because we have the first sentence, the user is active. So we may have the other status inactive. Okay, how about at least the one network link not available? Okay, so we don't need to consider one network link. We only need to consider how to express the network link will be available. So we can use S of nx. That means network n is x. So x means available or not available. Okay, so because we have different network links for two different stations, maybe we have the first network link or second network link or third network link. Okay, so we use n to indicate network link n, and for available and not available, we use the status variable x. Okay, once we have defined the variables, then we can translate the original sentence by this predicate variables. Okay, every mail messages larger than 1 MB will be compressed. Okay, so now you can see every mail messages. Okay, that means for all n is mail messages. When it's larger than 1 MB, it means mail of n1. For all messages, if the size is larger than 1 MB, then it will be compressed. Then it's C of n. Okay, that's for all. If a user, that means for some, right? Because we are dealing with particular users. Okay, so for some U, because U is the user. If the user is active, that means this is U, A of U, that means the user is active. If the user is active, then at least one network link will be available. Then exists n s of n in status is 0. Okay, so now you can see we have more flexibilities to describe a sentence within the domain. Every mail messages for some users. Okay, so you can see that gives us more range or different ways to express the original English sentence and express by predicate logic.
All right, next let's see how we translate the following premises and conclusions by predicate logic.
Okay, so let's see this example. This example is very famous. We call that Lewis Carroll example. All lions are fierce. Some lions do not drink coffee. And then we can draw the conclusion. Some fierce creatures do not drink coffee. Okay, intuitively this is right, right? Because if all lions are fierce, and some lions do not drink coffee. So we have the range. If this the universal or the domain is lions, okay, and it tells us all lions are fierce. Okay, so all lions they are fierce. Okay. And then some lions do not drink coffee. That means some lions drink coffee and some lions do not drink coffee. So maybe we can partition the domain to two different parts. The first part drink coffee, and the second part not drink coffee. Okay. So this tells us some feared creatures do not drink coffee, right? Because all of them are fierce. So for all these fierce creatures, some do not drink coffee. So that means so intuitively, this example from two premises to the conclusion, we can see the inference is correct. In next sessions, maybe next sessions, we will verify how to draw the conclusions from the premises. So let's see how we transform this sentence into practical logic. Okay, once we use L of x, if x is a lion, f of x is fierce, c of x is x drinks coffee. Okay, and then all lions are fierce. Remember, all lions for all x, if x is lion, then x is fierce. That means all lions. Some lions do not drink coffee. For some, they share the same properties. This is lions and this do not drink coffee. Okay, so for some x, L of x, and not C of x. Okay, so you can find a particular instance. It's a lion and does not drink coffee. That means some lions do not drink coffee. So we have a very similar sentence. Some fierce creatures do not drink coffee. That gives for some x f of x and not c of x. Okay, so it's the same sentence. Alright, so if you remember how we apply propositional equivalence, we need to write equivalent form from A to A1, A1 to A2, and maybe AN to B. Then we can infer that A is logically equivalent to B. Now we have practical logic, so we can do a very similar thing to infer that these two premises can draw a conclusion. Okay, so we will see this later. All right, that's the end of this section 1.4. Anything we need to explain again, maybe in Chinese? 有没有什么不了解的地方可以用中文再讲一遍？好，这个问题第二遍了。好，没有问题，我们再讲一次哈。好，我们来看一下 for all x L of x and f of x， 这个东西跟这个东西有什么不一样？好，那我们再讲一次哦。这句话代表什么？对于所有的 x， 它是狮子，而且它是凶猛的动物。所以是什么？所有的狮子都是凶猛的动物，对不对？好，那我们下面讲的呢，是所有的 x， 只要它是狮子，它才是凶猛的动物。所以我们的 universal 可能有这个狮子、大象、老虎，我们有好多动物在这个种类里面。那这句话告诉我们，如果它是狮子，那它就是凶猛的动物。那其实我们是这样，但是这一种告诉我们，所有的 x 都是狮子，所有的 x 都是凶猛的动物，所以这个所有的东西都是狮子 and 凶猛的动物。那这两个是不一样的，这样。 好，还有没有其他的问题？好，没有的话我们就下周见喽。See you next week.